On the 22nd of December 1938, a museum curator picking through a pile of discarded fish on a South African dock reached into the heap and pulled out an animal that had been extinct for 66 million years. Marjorie Courtenay Latimer sent a sketch to an ichthyologist named J.L.B. Smith, and what he wrote back would undo an assumption the entire fossil record had been resting on without anyone noticing it was there. What she had pulled out of the pile was a coelacanth. It was about 5 feet long and weighed roughly 127 pounds, steel blue with pale flecks across the scales, and its fins were not fins in the way any living fish has fins. They hung off the body on thick fleshy stalks that moved like limbs. It had an extra lobe on the tail that she described as looking like a small dog's tail, and when the trawler hauled it up out of the water, it had still been alive, snapping at the crew. This meant the animal in front of her was not supposed to exist anywhere on Earth. Coelacanths were known from fossils. The fossils stopped in the Cretaceous. Nothing in the rock recorded them after the extinction that killed the dinosaurs. Every textbook placed their disappearance at the same boundary, and this one had been swimming off the mouth of the Chalumna River that morning. The fossil record was treated as a reliable ledger of what had lived and what had stopped living. A lineage appeared in the rock, persisted through a set of layers, and then vanished. The vanishing was read as the end of the animal. Absence from every subsequent layer, across every continent, over tens of millions of years, was taken as proof of extinction. It was the single most basic inference in paleontology, and it was applied to thousands of species without anyone treating it as a question. But there was one thing the ledger could not record. Absence of a fossil is not absence of an animal, and the size of the gap it left here is almost impossible to hold in the head. Coelacanths did not survive quietly for a few thousand years past the boundary. They survived for 66 million years without leaving a single fossil anyone had found. The lineage Courtenay Latimer held on that dock had been continuously alive, generation after generation, through the entire span that produced primates, and grasses, and the Alps, and the human species. Nothing in the rock recorded any of it. Smith named the genus Latimeria after her, and the species Chalumnae after the river. And then he did something that tells you how badly he needed a second one. He printed reward posters in English, French, and Portuguese, offering £100 for another specimen, and had them distributed along the entire east coast of Africa. At the time, that sum was more than a subsistence fisherman would see in a year. Then he waited 14 years. Here is what that wait cost him. Smith had been away for the Christmas holidays in 1938 and did not see her letters for weeks. The fish began to rot. East London had no cold storage that could take something that size, so the only way to keep any of it was to hand the specimen to a taxidermist, and the taxidermist did what taxidermists do. The skin and skeleton were preserved and mounted. The internal organs were thrown away. For 14 years, the most significant animal discovery of the century could only be examined from the outside. The reward was claimed in 1952 by a Comoran fisherman named Ahmadi Abdallah. Smith persuaded the South African Prime Minister to send a military aircraft to collect it, and he wept on national radio, describing the moment the crate was opened. He was so certain this second fish was a different animal that he named it after the Prime Minister who had sent the plane, largely because it appeared to be missing its first dorsal fin. It was later established that the fin had been lost to an injury early in the animal's life. It was a coelacanth like the first one, and the Comorans were baffled to be paid for it. They had a name for the fish. They called it gombessa. They caught it by accident. They considered the flesh nearly inedible unless dried and salted, and they used the rough scales as an abrasive for sanding. And if the animal was ordinary to the people who lived above it, what exactly was discovered in 1938? How many species classified as extinct at a specific boundary are simply the ones that stopped leaving fossils? A second living species was found off Sulawesi in Indonesia in 1997, nearly 6,000 miles from the Comoros, and described as Latimeria manatoensis. Jacques Millot spent more than 2 decades on Comoran specimens before publishing a 3-volume anatomy. The mounted skin from that first fish is still in the East London Museum. Everything that would have answered the first questions anyone asked went into a bin behind a taxidermist shop in 1939, and nobody wrote down what was in it. Number 2. The moa. In 1839, a doctor named John Rule carried a 6-inch piece of broken bone into a London lecture room, and the anatomist he handed it to told him it was a scrap of ox bone off somebody's kitchen table. Richard Owen changed his mind after the lecture, and what he then did with that fragment would either destroy his professional reputation or establish that comparative anatomy could reconstruct an entire unseen animal from a single broken piece of one. What he had in his hand was a section of femur shaft. It was thick-walled and dense, with the internal architecture of a bird rather than a mammal. It was heavy for its size. It carried none of the hollow lightning that flight requires, which meant whatever grew it did not fly. And the diameter of the shaft placed the animal somewhere in the range of an ostrich or larger. That put Owen in an impossible position. New Zealand had been in European contact for roughly 70 years. No settler had reported a giant bird. No explorer had shot one. No skin, no feather, and no second bone had ever reached Europe. The islands were understood to have no large land animals at all, and Owen was about to claim, from one fragment, that they had carried a flightless bird the size of an ostrich. The method he was using had a name and a pedigree. Georges Cuvier had established that an animal's parts are so tightly correlated that a trained anatomist can infer the whole from a piece, and the principle had been treated as the crowning achievement of comparative anatomy. It was the reason museums employed men like Owen. It was what made a bone fragment a document rather than a curiosity, and it carried weight well beyond zoology, because the idea that every part of an animal implies every other part was read by many as evidence of design. But there was a problem underneath that authority. Cuvier had died in 1832, and his own successor in Paris had spent the years since arguing publicly that the method gave no genuine predictive power at all. The whole principle was live and contested at exactly the moment Owen picked up the fragment. He staked himself on it in the most exposed way available. He wrote that he was willing to risk his reputation on the statement that a bird nearly the size of an ostrich had existed, and possibly still existed, in New Zealand. The Zoological Society's publication committee refused the paper as too speculative. It appeared only after Owen agreed in writing that responsibility for it rested with him alone. His rival Gideon Mantell was among those unconvinced. And then he had to wait. Here is the part the confidence could not supply. He had nothing else to work with, and no way to get more except by asking. Owen wrote to settlers, missionaries, and colonial officials asking them to look for bones. 4 years passed. Then, in 1843, the crates began arriving in London, sent back by collectors working riverbanks and dune systems, among them the missionary William Colenso and William Williams on the east coast of the North Island. There were not a handful of bones. There were enough to assemble complete skeletons from more than one species. Owen named the group Denornis, meaning terrible bird. The bones kept coming for decades, in quantities that let anatomists argue about how many species there had been, and the Victorian public took to the moa harder than it had taken to the dinosaurs a few years earlier. The largest of them stood taller than a man with the neck extended, and he was photographed decades later beside a mounted skeleton of one, holding the original fragment in his right hand. This is where one bone stops being about one man's reputation. If 70 years of European settlement produced no report of an animal that stood 9 feet tall, how recently did it have to disappear for that silence to make sense? And what happened in the gap? Moa were alive when Polynesian settlers reached New Zealand. The archaeology shows them hunted, butchered, and cooked in earth ovens across the South Island, with bone middens large enough to map. Every species in the group was gone within a few centuries of human arrival. Owen got the size right, the posture roughly right, and the classification right, from 6 inches of shaft. Nobody knows what sound it made. No European ever heard one. The people who did hear them left no description of it that survived, and the bird has been rebuilt from the bones twice over and will stay silent. Number 3, the platypus. In 1799, the keeper of natural history at the British Museum took a pair of scissors to a specimen that had just arrived from Australia and started cutting, looking for the stitches. George Shaw was not a crank, and he was not being unreasonable, because the object in front of him was exactly the kind of thing that had been arriving from the East for decades, specifically to make men like him look foolish in print. What he was cutting into was a dried pelt with a bill on it. The body was small and covered in dense fur like a mole. The feet were webbed. The tail was broad and flat like a beaver's, and where the head should have ended there was the flat, leathery bill of a duck, which Shaw described as looking like a duck's beak grafted onto the head of a four-legged animal. That put him directly in the path of an industry. Fake animals were a real trade with real customers. Craftsmen in Asia and the Middle East were stitching monkeys onto fish and selling them as mermaids, and those objects reached Europe along the same shipping routes as this pelt. Barnum would later exhibit one to paying crowds. Respectable museums held others. And this specimen had traveled to London by way of India, which was the exact corridor the fakes came in on. The scientific establishment had a working defense against this, and it was a sound one. A hoax is an assembly. Assembly leaves a join. Find the join, expose the seam, and the object collapses back into its component animals. Shaw applied the test properly, cutting along the boundary where the bill met the skull, which is precisely where a forger would have had to make the attachment. He found no stitches. He found no adhesive. He found no seam of any kind, because there was not one. But a clean result was not the end of the problem. It was the start of a much longer one. Shaw published the description anyway, and published his doubts alongside it, writing that it was impossible not to entertain suspicions about the animal's genuineness and to wonder whether some deception had been practiced in its construction. He named it Platypus anatomist, flat-footed duck, and with the question of whether it was real closed, the question of what it was stayed open for another 85 years. The animal has fur and produces milk, which makes it a mammal. Settlers in Australia said it laid eggs. Aboriginal peoples across eastern Australia had said so for far longer, and knew its burrowing, its nocturnal habits, and the venomous spur on the males, all of which European science would need decades to confirm independently. None of that was accepted. Mammals do not lay eggs. The claim was considered improbable on its face, and zoologists held out for proof. And that is the point where the seam test shows what it was actually worth. It could establish that nobody had sewn the bill on. It could not establish a single thing about how the animal lived or reproduced. Proof arrived on the 29th of August, 1884, when a Cambridge zoologist named William Caldwell, working in Queensland with Aboriginal trackers catching specimens for him, shot a female between the laying of her 2 eggs and could finally see the developmental stage. He sent a telegram of 4 words: monotremes oviparous, ovum meroblastic. It reached the British Association meeting in Montreal on the 2nd of September, and the reading was interrupted by applause. Eggs, developing like a reptile's. And that changes what the 85 years were made of. If the answer had been available from people living alongside the animal the entire time, what was the scientific establishment actually waiting for? The platypus was eventually placed in an order created specifically to hold it, and the echidnas, because no existing category would take it. Part of the delay was the specimens themselves. What reached Europe were dried skins and preserved fragments, and features that would have settled the argument early, including the mammary glands, were not obvious in material in that condition. The venomous spur was documented. Electroreception in the bill, the sense it uses to hunt with its eyes and ears shut by detecting the electrical fields of muscle movement in mud, was proposed in the 1980s and confirmed experimentally. The genome was sequenced in 2008 and turned out to carry venom genes recruited from the same families reptiles used, independently. Shaw was right to look for the stitches. That was good practice, and the same instinct catches real forgeries. He had no way of knowing that the thing on his bench had been assembled by something with considerably more time than a forger. Number 4. The Komodo dragon. In 1910, a Dutch lieutenant stationed in the eastern Indonesian islands kept hearing the same account from sailors and villagers, that there was a crocodile living on the land, on an island, that never went into the sea. Jacques Carrel Henri van Steen van Hensbroek decided to go and look for himself, and what he brought back would show that an animal could reach the size of a large predator and stay entirely unrecorded by science inside a well-charted archipelago. What he came back with was a photograph and a skin. The animal was a monitor lizard. That first specimen ran to around 7 feet, with heavy limbs, loose folded skin hanging at the neck, and a long muscular tail roughly equal to the body. It had a deeply forked tongue that it used to taste the air. The claws were built for digging and holding, and it was a fully terrestrial predator on an island of a few hundred square miles. This meant the local name had been almost right and completely misleading at once. The islanders called it Buaya Darat, land crocodile. It was not a crocodile. It was not related to crocodiles. It was a lizard, from the same broad group as the monitors found across Africa, Asia, and Australia, at a fraction of the size. It was the largest lizard alive anywhere on Earth, and the largest individuals reached 10 feet and close to 300 pounds. The scientific position on giant lizards was clear, and it rested on real evidence. Fossils of enormous varanids had been coming out of the ground since the middle of the 1800s. They were understood as a feature of the deep past, part of the same vanished world as the giant marsupials and the moa. The living monitors were the modest remnant of that lineage. The giants were finished, and this was not a guess, but a reading of the fossil record of 2 continents. Here is what that reading had no room for. The giants were not finished. Uwins, the director of the Zoological Museum at Bogor on Java, received the skin and the photograph along with 2 further specimens from a collector, and published the formal description in 1912 as Varanus komodoensis. Interest moved fast after that. An American named Douglas Burden mounted an expedition to Komodo in 1926. He came back with dead specimens for the American Museum of Natural History and 2 live animals, and the account he wrote of a giant reptile on a remote island fed directly into the popular imagination of the period. The animal had gone from a rumor among fishermen to a Western spectacle in 16 years. The first 2 living specimens reached Europe in 1927, when the London Zoo opened its reptile house, and Joan Beauchamp Proctor demonstrated one at a scientific meeting of the Zoological Society the following year. And the deeper explanation turned the whole story inside out. For most of the last century, the accepted reading was island gigantism. The animals had grown large in isolation, filling the top predator role on Komodo and its neighbors, the way island species often do, hunting the dwarf elephants that once lived there. Then more fossils came out of Australia and Timor. The oldest remains of this exact species come from mainland Australia, from around 3 million years ago, and those animals were already the same size. The lizard did not become a giant on the island. It arrived as one, and the islands are simply where it outlasted the mainland populations. And if an animal that size held out unrecorded until 1910, the question is what the record was measuring. How many islands in that archipelago had never had a naturalist set foot on them? And how many animals in the fossil record filed as terminated are only the mainland half of a longer story? 17 years passed between the first skin reaching Java and the first living animal a European scientist could stand in front of. The people of Komodo had words for it the entire time, more than one of them, in more than one language. The naming that entered the literature came from a museum director on another island, working from a photograph, a skin, and 2 specimens somebody sent him. Number 5. The giant squid. At 9:15 in the morning on the 30th of September 2004, a camera hanging on a line nearly 3,000 feet below a small Japanese fishing boat photographed something taking the bait, and for the next 4 hours, it did not let go. Tsunemi Kubodera and Kyoichi Mori had spent 2 years and 23 separate deployments getting to that frame, and what came up on the line would settle a question that had been open since sailors first started describing it. What the camera had caught was a giant squid. The animal was around 26 feet long. 2 of its 10 appendages are feeding tentacles far longer than the rest, and it was these that hit the bait. The suckers along them carry rings of serrated chitin that grip and hold and do not release. Its eyes are among the largest of any animal that has ever lived, built to gather whatever light exists at that depth. Its flesh is saturated with ammonium chloride, which is lighter than seawater and holds the animal in the water column without effort, and which also makes it inedible to almost everything that is not a sperm whale. And the camera recorded it more than 500 times while it fought the line. This meant the animal did not behave the way the science had assumed. The prevailing view held that a squid that size, in cold water with almost nothing to eat, would be a slow drifter, hanging in the water column and taking whatever came within reach. The photographs showed an active hunter attacking horizontally and wrapping its tentacles around the target. It struggled for over 4 hours. When it finally tore free, it left roughly 18 feet of severed tentacle on the line, still moving. For centuries, the scientific response to sea monster reports had been consistent and, on the evidence available, reasonable. Sailors described enormous, many-armed creatures dragging at ships and pulling men off decks. Those accounts came from men who had been at sea for months, in poor light, with a professional interest in a good story. The Norse kraken, the Scylla of the Odyssey, the various sea serpents, all of it was treated as one continuous body of maritime folklore. And folklore is not evidence. There was no specimen. But the folklore was never the thing that settled it. Bodies were. Pieces of these animals had been washing onto European beaches for a long time, and in 1857, the Danish zoologist Japetus Steenstrup gathered the strandings together with a very large beak and formally established the genus. 4 years later, a French gunboat encountered one at the surface and recovered part of it, which pushed the animal further into scientific respectability. A run of strandings on the coasts of Newfoundland in the 1870s put whole specimens in front of naturalists. From that point, the giant squid was not a legend. It was a described animal with a scientific name that no zoologist disputed. And then almost nothing happened for 150 years. Here is what makes the 2004 photograph genuinely strange. Close to 600 specimens had been recorded by then. The animal was in every textbook. Its anatomy was known, its beak was known, its buoyancy chemistry was known, and the circular scars it leaves on the skin of sperm whales had been measured. What nobody had done, in the century and a half between Steenstrup and that morning, was watch one alive in its own habitat. And that gap changes what a described species actually means. If an animal can be named, cataloged, dissected, and taught for 150 years without one human being observing it alive, what exactly was known about it? The first film of one in the deep came in 2012. The first footage in United States waters came in 2019 in the Gulf of Mexico. Across the whole of human history, with every technology now available, this animal has been recorded alive in its own environment a handful of times. Nobody has watched one hunt anything but bait on a line. And the largest individuals are not known from bodies at all. They are inferred from the diameter of sucker scars on whales that came back up, which means the biggest ones on record have never been seen by anybody and exist only as marks left on something that survived them. Number 6. The Okapi. In 1900, a British colonial official in Uganda sat down with a group of Mbuti men from the Congo forest, asked them about an animal he had spent years hearing rumors of, and they told him its name. Harry Johnston had been chasing a creature Henry Morton Stanley mentioned in a footnote, and the answer he got that day exposes what the scientific record had actually been measuring for the previous 50 years. What the Mbuti described, and what Johnston eventually obtained, was an animal with the body of a horse and hindquarters marked in horizontal white stripes. It stands around 5 feet at the shoulder. It has a dark purple-brown coat with an oily sheen that sheds rain in a forest where it rains constantly, a tongue long enough to reach its own eyes and clean them, and cloven hooves. The males carry short skin-covered horns on the skull. It moves almost silently. That combination placed it nowhere. The stripes suggested a zebra, so when Johnston sent home the first material he had, which was 2 strips of skin, Philip Sclater proposed a forest horse and named it after him in the genus Equus. Then in March of 1901, a complete adult skin and 2 skulls arrived, forwarded through a Belgian officer at a Congo station. The skulls settled it. The teeth were wrong for a horse. The ankle bones carried a structure that occurs in exactly one family. It was not a horse, and not a zebra. It was the only surviving close relative of the giraffe, an animal whose lineage had been assumed to be finished except for the giraffe itself. And that is where the record becomes a statement about the people keeping it, rather than about the animal. It had a name in the Mbuba language and a name in the Lesse language before any European heard of it. The Mbuti hunted in the same forest and could describe its tracks, its diet, and its habits. Stanley crossed the Ituri forest 3 times. He recorded the Mbuti word in a footnote in 1890, noting only that the Mbuti had identified his own pack donkey with an animal they already knew. Asked about it later, He said he believed the animal existed because of the numerous tracks he and his men kept finding, pressed into the wet clay of the forest floor. Lancaster concluded afterwards that Stanley and his companions had probably caught sight of the animal itself on those crossings, without registering what they were looking at. None of that counted as knowing, but here is what the standard was quietly requiring. Not proof, custody. What Johnston needed was not information about the animal, it was pieces of the animal, in a crate, in London, on a table in front of the Zoological Society, which met on the 7th of May 1901, and put the skin and the two skulls on display. Only at that meeting did the animal begin to exist. And the naming preserves exactly what happened. Sclater presented a painting of it to the Zoological Society before anyone in London had seen the complete skin, and the confusion over what it was ran on for months, with Johnston himself proposing that it belonged to a genus of extinct giraffids. Ray Lancaster established a new genus, and the species became Okapia johnstoni, and he went on revisiting his own classification of it afterwards. The genus is the Mbuti word, slightly altered in the mouth of a European. The species name is the British official who forwarded the specimens. The people who had known the animal for generations supplied the noun. The man who put it in a box supplied the surname. And that pattern is not confined to one animal. If the standard for existence was a specimen in a European institution, rather than reliable knowledge of the living animal, then the record of what was discovered and when is a record of shipping, not of knowledge. How many entries in the catalog have a discovery date that is really an arrival date? Around 30,000 okapi are estimated to survive in the Congo forest, and they remain close to impossible to observe in the wild. The Mbuti were the source, the guides, and the reason Johnston found anything at all. Their word survives in the genus. Not one of their names does. Number 7. Homo floresiensis. On the 2nd of September 2003, a team digging in a limestone cave on the Indonesian island of Flores came down on a skull about 20 feet below the floor, and it belonged to a fully grown adult with a brain roughly a third the size of yours. The team at Liang had gone there looking for traces of modern humans moving through Asia toward Australia, and what came out of that trench instead put a second kind of human being on an island alongside our own species, far more recently than anyone thought possible. What they recovered was a partial skeleton, labeled LB1. The individual was female, around 30 years old at death, and stood about 3 feet 6 inches tall. The brain case holds roughly 400 cubic centimeters. The teeth were all permanent, which is what told the excavators they were not looking at a child. The feet are long relative to the legs. The wrist bones are shaped like those of hominins millions of years older, and the remains were not fossilized at all. They were still soft, and one description compared the consistency to wet blotting paper. That put the find in a category with almost nothing else in it. Small brains in the human lineage are old. 400 cubic centimeters is Australopithecine territory, the range of animals that lived in Africa millions of years before anything resembling us. This individual was not millions of years old. Continued excavation produced fragments of at least 13 more individuals from the same cave. Stone tools lay alongside them, and the initial dates put the youngest material at around 12,000 years ago. Nothing in the accepted account of human evolution had room for that. Our species had been the only human on Earth since the Neanderthals ended, and that solitude was treated as one of the basic facts of the recent past. Every other lineage had closed. Neanderthals were gone. Homo erectus was long gone. The idea that another kind of human had been alive on an island within the last 20,000 years, making tools, small-brained, 3.5 feet tall, was not an adjustment to the picture. It contradicted it outright. But the objection that followed was not about the picture. It was about the bones. A number of researchers argued, some of them forcefully, that LB1 was not a new species at all, but a modern human with a pathology. Microcephaly was proposed first. Then Laron syndrome, a form of pituitary dwarfism. Then Down syndrome, in a paper published a decade after the original description. The argument has real substance behind it. A single skeleton with unusual proportions is a thin basis for declaring a species, and the history of paleoanthropology contains examples of exactly that mistake. The counter-argument is the other individuals, which show the same small body size rather than one anomalous case, and a separate site on Flores called Mata Menge, which produced jaw and tooth fragments from what may be an earlier form of the same lineage at around 700,000 years old. If that reading holds, small-bodied hominins were on Flores for an extremely long time, and the stone tools at Mata Menge undercut the claim that the tool-making at Liang required modern humans. But there's a second problem that changes the shape of the whole thing. The dates themselves moved. Cave deposits are stratigraphically messy. Material shifts vertically and horizontally through them by flooding, erosion, burrowing, and simple gravity. And by 2015, far more was known about the Liang sequence than in 2003. The revised figures published in 2016 put the skeletal material between roughly 60,000 and 100,000 years old, and the associated stone tools between 50,000 and 190,000, not 12,000. And this is where the folklore has to be handled carefully rather than enthusiastically. Flores has stories about the Abu Gogo, small hairy cave dwellers with an odd gait. Those stories were repeated everywhere after 2003 as a possible surviving memory of this species, and under the original dates the connection was at least arguable. The revised dates make it considerably harder, because they push the last evidence at Liang back to roughly the point modern humans were arriving in the region. The bones are real. The debate about what they are is a real scientific debate, with competent people on both sides. The folklore is a separate matter and has not been shown to be about them. Whether they were still alive when the first modern humans reached Flores is an open question with nothing in the ground to answer it yet. What is in the ground is a woman who stood 3 feet 6 inches tall, and nobody knows whether anyone like us ever saw her people. Number 8. The Yeti. In 2012, an Oxford geneticist put out a public call asking anyone in the world holding physical material from an unknown ape to send it to him for genetic testing. Brian Sykes was offering the thing a century of expeditions and photographs had never produced, which was a method that returns an answer rather than an argument. What came in was hair. Roughly 30 samples arrived, collected across decades and continents, some from museums, some from mountaineers, some from private collections, along with material described as teeth, skin, bone, and droppings. 2 came from the Himalayas. 1 had been taken from an alleged mummified specimen in Ladakh, shown to a French mountaineer around 40 years earlier. The other was a single hair found in a high-altitude bamboo forest in Bhutan, roughly 800 miles east of the first. This was the first peer-reviewed genetic survey ever conducted on the question. Every previous line of evidence had been the kind that cannot be closed. Footprints in snow melt and enlarge. Photographs are ambiguous at distance. Eyewitness accounts cannot be tested against anything. Sykes was using mitochondrial sequencing with rigorous decontamination, and that either matches a known species or it does not. The finding, when it came, was concrete and it went around the world. 28 of the samples matched ordinary known animals, including bears, wolves, cows, raccoons, and 1 human. The 2 Himalayan samples matched no modern bear. Their closest genetic affinity was to a Paleolithic polar bear specimen from Svalbard, at least 40,000 years old. Sykes suggested a possible unknown bear species, or a polar bear and brown bear hybrid, still living in the Himalayas, and said the next step was to go and find one. But the proof everyone reported was never actually proof. The result did not survive review. And the reason is technical rather than dramatic. The identification rested on 104 base pairs of a single mitochondrial gene. 2 researchers published a comment in the same journal pointing out that a fragment that's short cannot reliably separate brown bears from polar bears, because at that length the sequences overlap. A second paper made the same argument independently and noted that polar bears do not live in the Himalayas, while Himalayan brown bears do, and that the sample colors matched them. Both concluded the economical reading was brown bear with some DNA degradation. Then in 2017, a separate team sequenced far larger portions of the mitochondrial genome from 9 samples attributed to the Yeti. The results came back as Asiatic black bear, Himalayan brown bear, and Tibetan brown bear. The one exception was a tooth from a specimen displayed as a relic. It was a dog, And this is the item that has to be here honestly. Every other creature on this list was confirmed by a specimen. This is what it looks like when the test is finally run, and the answer comes back negative. The evidence submitted was real material, the analysis was competent, and the thing described in the accounts is not what produced the samples. Sykes made a point worth stating plainly, which is that none of this proves such an animal does not exist. It proves that the physical evidence people had been holding on to and pointing at came from bears. That was the material. It was tested, and it was bears. Whatever anyone saw on those slopes, nobody brought back a piece of it, and the pieces they believed they had brought back belonged to something else. Number 9. The Denisovans. In 2008, Russian archaeologists working in a cave in the Altai Mountains of southern Siberia recovered a fragment of a child's fingertip, and the DNA inside it belonged to a kind of human being nobody had ever known existed. The bone went to Svante Pääbo's laboratory in Leipzig, and the sequence they pulled out of it did something no fossil had done before, which was to establish an entire population of humans on genetic evidence alone. What that fragment yielded was a genome. Not a fragment of one, and not a mitochondrial sketch, but a nuclear genome sequenced well enough to place the individual on the human family tree with confidence. The results showed a population sharing a common ancestor with Neanderthals, and splitting from them, distinct from Neanderthals and from us. A molar recovered from the same cave carried closely matching mitochondrial DNA and came from a different individual in the same group. And that tooth had a shape unlike a Neanderthal tooth or a modern human tooth, resembling instead hominins far older. This meant a human population had been defined without a face. There is no Denisovan skull from that cave, no complete jaw, no pelvis, no rib cage. The physical remains from the site amount to a fingertip fragment, a few teeth, and pieces of bone. Everything known about them as a population came out of the chemistry inside those pieces. They still have no agreed scientific name. The way species get recognized in paleoanthropology had been settled for well over a century. You need morphology, a type specimen, described and measured, carrying features that distinguish it from everything already named. That is what Homo neanderthalensis rests on, and Homo erectus, and Homo floresiensis. Bones define the species, and everything else is commentary on the bones. Here is what that requirement was about to lose. The genome outran the skeleton. The worst part is not that there was no skull. It is what the genome found when it was compared against people who are alive. Denisovan DNA is in modern populations right now. Melanesians in Papua New Guinea carry roughly 4 to 6% of their genome from this group. Aboriginal Australians and some populations across South and Southeast Asia carry it too. Analysis of DNA from people in Indonesia and New Guinea, published in 2019, suggested interbreeding may have continued as recently as 15 to 30,000 years ago, which would make Denisovans the most recently living human species other than our own. And in one case, the inheritance is not passive. The variant of the gene EPAS1 that allows Tibetans and Sherpas to function at extreme altitude without the blood thickening that would kill a lowlander came from Denisovans. It is not a relic. It is load-bearing physiology in living people. And this is where a fingertip stops being a fingertip. If a population can be identified, mapped across a continent, and located inside the bodies of people alive today, all from bones that would fit in a coffee cup, what is the fossil record actually counting? A partial lower jaw found in a Tibetan cave in 1980 sat unidentified for decades. It came from Baishia Karst Cave in Gansu Province, at over 10,000 feet on the Tibetan Plateau, and only the right half of it survived. No DNA was left in it at all. What the team extracted instead were proteins, taken from one of the molars, degraded enough to be clearly distinguishable from any modern contamination, and the protein sequences matched the Denisovans from the Siberian cave. The dating put it at around 160,000 years old, which makes it the earliest hominin fossil known from the plateau, and means Denisovans were living at extreme altitude long before modern humans arrived there. That is also the environment the altitude gene came out of. Further material has since been identified from caves in China and in Laos, and a cranium recovered in Harbin in 1933, hidden in a well for decades before it reached scientists, has been associated with the same lineage. Pabo received the Nobel Prize in 2022 for the work that made any of it readable. We can read their genome and we cannot draw their face. There is no reconstruction anyone can defend because the pieces that would carry a face have not been found. And the people walking around today with their DNA in their lungs and their blood have no idea what the ancestors who gave it to them looked like. Number 10. The Saola. In May 1992, a survey team walked into a hunter's house in a nature reserve in northern Vietnam and saw a skull on the wall with two long straight horns that belonged to no animal known to science. The team was a joint Vietnamese and WWF survey working the forests of Vu Quang near the border with Laos, and what they were looking at was the first genuinely new large mammal to enter the scientific record in over 50 years. What the skull turned out to belong to is called the Saola. The animal stands about 3 feet at the shoulder. It is dark brown with sharp white markings on the face, and the two horns are nearly parallel, gently curved, and reach around 20 inches. It has the largest scent glands of any living mammal, set on the face beneath a flap it can open. DNA analysis showed it was not an antelope at all. It is a bovid, related to wild cattle, and different enough from everything else alive that it required a new genus of its own. That put it in a category with one other animal. New mammals are described constantly, but they are rodents and bats and shrews, small things, in places nobody had sampled properly. A new genus of large mammal is a different order of event entirely. The last one before this was the okapi in 1901. 91 years separate them. This is where the pattern running through this entire list should have continued. Every other creature here was confirmed by physical evidence and then studied. The coelacanth was dissected in 1952 and had a 3-volume anatomy written about it. The moa was rebuilt from crates of bone. Komodo dragons went into the London Zoo in 1927. Okapi are in zoos on 4 continents today. The proof arrives, the argument ends, and the science begins. The proof arrived and the science never started. The Saola has never been studied alive. At least 13 individuals have been taken into captivity since 1992, and every one of them died within months. The species does not tolerate confinement, and nobody knows why, because there is no baseline to compare the veterinary work against. Its reproduction is undescribed. Its diet is inferred rather than observed. Its social behavior is guessed at. And here is what that means on the ground. Almost no biologist has ever seen a living Saola in the wild. The last confirmed record of any kind is a single camera trap frame from the 7th of September, 2013, in Quang Nam Province, showing one animal at the edge of the shot at sundown. Nothing since, despite thousands of camera trap nights across the range. The IUCN assessment puts the population at fewer than 750 and possibly under 100, and specialists working on it will tell you the real figure may be far lower than that. The threat is not targeted hunting. It is wire snares set for deer and civets, laid in the thousands across the forest floor, catching whatever walks into them. And if the first new large mammal genus in 91 years can be found, named, and then vanish before anyone learns how it lives, what does a discovery date actually mark? The okapi was described in 1901 and can be watched in a zoo this afternoon. The Saola was described in 1993 and has never been kept alive for a year. Fewer people have seen one in the wild than have stood on the summit of Everest. It was proved real in a hunter's house. From a skull belonging to an animal somebody had already killed. The species may go extinct before a single scientist has watched one live, and if that happens, the entire record of it will be a pair of horns on a wall, a handful of camera frames, and a genus name for something nobody ever got to know. That is where this one still sits. There are more. Subscribe if you want to see them.